We now look at a form of coding which is basically mean or average coding. This is a form of coding which affords more than average lossless data compression. Now we are all familiar with the term, with the arithmetic progression, the geometric progression, and the harmonic progression, as well as the associated means such as the arithmetic mean, the geometric mean, and the harmonic mean. Now, if A is the initial term and the common difference is D, then the arithmetic progression is A plus D, A plus 2D, and so on. Likewise, if the initial term is A and the common ratio is R, the geometric progression is AR, AR square, AR cube, and so on. For the harmonic progression, it is the terms are the reciprocal of the arithmetic progression. 1 by A, 1 by A plus D, 1 by A plus 2D, and so on. Likewise, if when it comes to the mean, we know that the arithmetic mean of two numbers A comma B is nothing but A plus B by 2. And likewise, the geometric mean of two numbers is nothing but square root of A into B. And although the harmonic mean is defined as AB by A plus B, for the sake of consistency, as we shall see later, I'll redefine it as 2AB by A plus B. By this slight redefinition, actually, it maintains the consistency between the means and the progressions for all the three series without upsetting or conflicting with the equality arithmetic mean greater than or equal to geometric mean greater than or equal to harmonic mean. Now, the interesting property of all these progressions and these means is that if any three terms are in arithmetic progression, the arithmetic mean of the extreme terms is equal to the middle term. A plus 2D by 2 is equal to A plus D. Likewise, for a geometric progression, if any three terms are in a geometric progression, AR square, the geometric mean of the extreme terms AR square is equal to the middle term AR. Likewise, if we redefine the harmonic mean like I just said, then if any three terms are in an harmonic progression, then the harmonic mean of those three terms, of the extreme terms, will be equal to the middle term, that is 2 times 1 by A times 1 by A plus D by 1 by A plus 1 by A plus D is equal to 1 by A plus 1 by A plus 2D by 1 by A plus 2D is equal to 1 by A plus D will be true. Another similar in general, if in any arithmetic progression, if any three terms are equidistant from it, if we take any three equidistant terms in an arithmetic progression, then the arithmetic mean of the extremes A minus D plus A plus D by 2 will be equal to the middle term A. Therefore, we have the arithmetic progression here A minus the three equidistant terms A minus ID, A plus ID. So you will have A minus ID plus A plus ID by 2 equal to A. Likewise, if we take any three equidistant terms in a geometric progression, then that you have AR power I minus C, AR power I, AR power I plus C, then the square root of AR power I minus C into AR power I plus C is equal to AR power I. Like similarly for harmonic progression also, if you take any three equidistant terms in a harmonic progression, the harmonic mean of the extremes would be equal to the middle term. Now your objective is to code a number n less than equal to m equal to 2 power L dash, where L dash is very, very large. The conventional coding of a number is using arithmetic mean, that is, we code 2 power I plus 2 power I plus 1 by 2 as the next number to compare with n in order to code it. Instead of using the arithmetic mean, if n is any number, then there is any unique integer I such that 2 power I less than equal to n, which is less than 2 power I plus 1. This will always be true. So we can use the arithmetic mean like we just saw, or we can use the geometric mean such that 2 power I into 2 power I plus 1 square root of this as for coding n, as for comparing with n. I and I plus 1 will, one of either I or I plus 1 will be the extreme values. So that, of course, later on subsequently while coding, the value will no longer be an integer, but that is alright. We'll have to take floating point approximation for that. Likewise, instead of this, we can use the harmonic mean, that is equal to 2 into 2 power I into 2 power I plus 1 by 2 power I plus 2 power I plus 1. So this is the, we can use this for coding it. Now we know that if any number n is there less than equal to 2 power L dash, there exists a unique I such that 2 power I less than equal to n less than 2 power I plus 1. Now instead of taking the mean of 2 power I, we can radically improve the lossless comparison by taking the mean of the exponent I alone. That is, in this case, even the arithmetic progression will give a excellent lossless. 2 power I plus 1 by 2 for the case of the arithmetic mean. For the case of the geometric mean, we could take 2 power square root of I into I plus 1, and in the case of the harmonic mean, we can take 2 power 2I into I plus 1 by I plus 1. So we can pair these methods together. One is 2 power I plus 2 power I plus 1 by 2 can be paired with the method 2 power I plus 1 by 2. This is your regular coding. This will give significantly better compression. This can be used for regular data compression. Likewise, if we use geometric mean, we can pair square root of 2 power I into 2 power I plus 1 with 2 power square root and 2 power I in square root of I into I plus 1. So these two methods can be paired. Since it's geometric, we could possibly use it for coding, losslessly coding video information. Likewise, with the harmonic mean also, we can pair these two methods together, namely 2 into 2 power I into 2 power I plus 1 by 2 power I plus 2 power I plus 1, or 2 power 2 into I plus 1 by I plus 1. So these two methods can also be used for all of these methods. This probably could be used for coding audio information. All these three methods provide excellent lossless data compression.